Okay, so next we're going to go over the questions that I made earlier. So the questions ask us to prove whether or not the following languages are regular. If a language is regular, we need to make a DFA or NFA for it. And if it's not regular, we use the pumping lemma to prove that. So what I'm saying is that in the exam, sometimes the questions won't straight up ask you to prove a language is not regular. It'll be more open-ended. So it'll ask you to say whether or not it is regular. So there's two possibilities. The language is regular or it's not. And so you need to think about that before you go on to answer the question, because you might try to prove that a regular language isn't regular, which will be impossible. You'll just be wasting all your time. So let's start off with the first question, which is this one. Oh, I already got pasted, never mind. So this is the language containing strings over alphabet AB, where the string has the same number of A's in it as B's. So for example, this would be in a language because there's 3 B's and 3 A's, and so it's the same amount of A's and B's. Whereas this would not be in the language because now there's more B's than A's. So the first step is to think about whether or not this language is regular. Well, I already know it isn't because I've seen this before, but still, you need to think about it in the exam. So one way to reason about it is to consider whether or not you think you'd be able to make a DFA for it. So let's try and think about what happens when we construct a DFA for this language. So for this question, for this language, we would need to try and keep track of the imbalance of A's and B's. We want states representing situations where we have more or less A's and B's. So the accept state would be where we have no difference between the amount of A's and B's. So the imbalance is 0. Then we need to keep track of when we have more A's than B's. So let's have a state for having one more A than B's. Okay, but we also have to keep track of the case where we have two more A's than B's. But we also might have three more A's than B's, so we need a state for that as well. And also we have to keep track of the case where we have more B's than A's. So this will be a state where we have one more B than A. And this goes on infinitely. We would need to have infinite states for every possible imbalance we could have. So we could have a million more A's than B's, and we'd need states for all of that. And so because the length of this of a string in this language can be anything, the imbalance of A's and B's can also be anything. And so a DFA for this language would actually require an infinite amount of states, which isn't allowed for DFAs because DFAs can only have a finite amount of states, right? And so intuitively, we can sort of see that a DFA for this language can't exist. Therefore, it shouldn't be regular. And so we want to prove that. And as mentioned earlier, to do that, we use the pumping lemma. So let me copy paste the boiler, the boiler page for the pumping lemma. One sec. Okay, there we go. Okay, so here's the boiler page. Before we continue, I wanted to mention something. I've rewritten the pumping lemma in a bit of a different way. I just rearranged some of the words to be on different lines. So one thing that you can notice about the pumping lemma is that it's in this format. We have a for all statement, then we have a there exists statement, then we have another for all, and another there exists. So this is what the pumping lemma's structure is like. The pumping lemma says that for all regular languages, there exists a pumping length such that for all strings in the language, with their length being at least a pumping length, there exists a breakdown where all three properties hold. So if you're finding it hard to memorize the pumping lemma, just think about this structure. Like for all, there exists, for all, there exists, like alternates between the two. So if you look at the boilerplate, we have that. So for all regular languages, there exists a pumping length such that for any, so for all, W and L, there exists. So it's the same structure. Okay, moving on to the proof. We need to select a string such that it is in the language and its length is at least n, and then show that there does not exist a single way of breaking it down where the three properties hold. So first, let's go over a string that might not be very wise to choose. So as mentioned before, we can usually use the second property to sort of constrain the amount of characters that x and y can possibly contain. So if we let w equal to a, b, a, n, b, n, well, this string has n plus 2 a's and n plus 2 b's. So it's the same amount. Therefore, it's in the language. And the length is definitely at least n. So we might think this could be a good string to choose for the proof. But the thing is, the first n characters of the string contain a mix of b's and a's. And so x and y can contain both b's and a's because the first n characters have those characters. Which also means that y can contain both b's and a's. And so there, because we want to prove that no breakdown of the string has these properties, we would need to consider all possible breakdowns. And in this case, we have to consider the breakdowns where y has only a's, and the breakdowns where y has only b's, and the breakdowns where y has a mix of b's and a's. And so with this string, there are three possible like classifications of breakdowns that we would need to consider, which is kind of complicated and it's a bit annoying in the proof, and we don't really want that. So instead of that, let's choose a string where x and y can at most contain one type of character. So to do that, we set the first n characters to be one character. So let's make it a. So this is an example of a string. So here, the first n characters are only a's. Therefore, x and y can only contain a's, and so y can also contain only a's. So there's only one possible breakdown to consider, and that's where y has only a's. So we've gone from three possible breakdowns to just one, and so using this sort of string is much simpler. So let's try it. This is going to be very similar to the other proof, but we're still going to do it nonetheless. So we know w is an L because the amount of a's is the same as the number of b's, and its length is 2n, which is definitely greater than n. And so by the pumping lemma, there must exist a breakdown. So therefore, there exists a breakdown. Sorry, I'm a bit sick. There exists a breakdown. W equals to xyz such that three properties hold. The next step is to write down the fact that x and y can only contain a's. So like reason about what the breakdowns will be. So by property 2, no matter how you break down w, w contains, oh sorry, xy xy contains only a's. And because of property 1, which says that y is non-empty, y must contain at least one a. Okay, and just to sort of say it again, the reason why we do this line of reasoning, where we conclude that y must only contain some sort of character, is because of the third property. So we're either removing or adding y, repetitions of y to the string. And so if we're trying to reach a contradiction, we want to know what y contains, because y is the thing we're repeating or removing, which is why we sort of try to reason about what y might contain. So we know y must contain at least one a. So y equals to a to the k for some k greater than or equal to 1. Okay, now we can either pump down or up and we'll still reach a contradiction. So let's just try pumping up. By pumping, we can pump up any amount of times for this one. Let's just do it twice. By pumping up 2 times, we get string x, y cubed, z. So we've pumped up y twice, so we added 2 repetitions of y. And y contains some amount of a's, so y equals to a to the k. Therefore, by pumping it up twice, we've added 2 of these to the start of the string. So we've added 2k a's. So xy cubed z is going to be this with 2k a's in addition. So we'll have a n plus 2k, because we've added 2k a's, bn. Now because k is greater than 0, so it's at least 1, n plus 2k must be greater than n, which means that this is no longer in the language, because this isn't equal to n. There's more a's than there are b's. So therefore, xy cubed z is no longer in the language, which contradicts this property, because it says that xyi, where I can be any number greater than 0, should be in the language. And we just got that xy cubed is not in the language, which is a contradiction. So this contradicts property 3 of the pumping lemma. By contradiction, our assumption was wrong. So this assumption was wrong. And so L is not regular. Okay, and that's the proof for this question. If something wasn't clear, just let me know. Okay, now we're going to move on to the next one.